Okay, so hi everyone. We did the project on CNO abundance in a nearby galaxy in the wavelength range from UV to optical. And we did it on one galaxy, Markarian 996, right here. It was part of the Galaxies survey, and it is a dwarf galaxy with known Wolf-Rayet stars, meaning that there are these very rare type of stars present that have very, very strong winds. They evolve from very massive stars, and they are just alive for a very short time before they die in a supernova. And we found that this galaxy is a nitrogen-enriched galaxy. So what we did was we investigated carbon, oxygen, and nitrogen abundances. And these are the UV and the optical spectra of the galaxy. And we kind of try to highlight the emission lines and the doublets and triplets and so on that we investigated.
So if we look at the lines that Lynn showed you, we may be interested in, for example, in the collisionally excited lines from some of the metals like oxygen, nitrogen, carbon, etc., because they help us trace the gas diagnostics, so temperatures and densities. And also there were some nice Balmer recombination lines that help us trace the dust extinction. So to do this, we want to measure the line fluxes and their errors. And to do that, we feed the lines with the LM-FIT package and using single or multiple Gaussian components. And you may think that this was super easy and we did it without problems, but it put us to the test. So we thank Zoraida for the line fluxes. And with the line fluxes, we input them into the Python package, which is a very neat package for the analysis of emission lines. As you can see from the right plot, basically PyNeb contains a lot of information on atomic and ionic physics. So it can plot nice Grothian diagrams, and it can measure emissivities of lines based on temperatures and densities, and it can vice versa estimate temperatures and densities based on sensitive line ratios. And so we use this to get gas diagnostics and measure the elements and ions abundances given temperatures and densities that we measured.
Okay, one of the main goals was measure the abundances of our galaxy. And to do that, we use the direct method that consists in compute the abundances using temperature and densities that are measured directly from our data. In each gas, we can always identify 3 or 4 ionization zones that contains different elements that are typical of that zone. That elements can be used to compute all the physical quantities of that zone. So first of all, we had to create our own table of the ionization zone. To do that, before you use PyNeb to check how much our elements ratio changed with temperature and density. As you can see from our plot, we have elements like O3 that are very sensitive to temperature, but very stable in density. On the other end, there are other elements as C3 that are very stable in temperature, but that are very sensitive to density. And of course, we have also elements that are sensitive both to temperature and density. So we use the most stable elements to compute temperature and density in each zone. That's our table. We use O3 to fix the temperature of the ionization zone. And then using the TT relation, we can add also the temperature of the other two zones. Then we use these two elements that were stable in density to fix the density. And to compute this measurement, we use the flux, putting it in PyNeb. Finally, we can use our temperature and density to have our abundances in each zone.
So using PINEP, we estimated the chemical abundances, well, the ionic abundances of different elements in our galaxies, and we first plotted the relationship between the ratio of the ionic abundances of the nitrogen and oxygen against the oxygen abundances of our galaxies. And in order to use as a reference, we also plotted in this diagram those same values, but for different galaxies in the chaos survey, as well as using galaxies from low and high redshifts. So if we focus on those two stars, this mark our galaxies abundances using different ions, as we have denoted in the legend of this table. We have the nitrogen 2 and oxygen 2 ratio, and the nitrogen 3 and oxygen 3 ratio. The fact that they are so far apart could be explained by the presence of very nitrogen-rich regions in our galaxy that are very highly ionized. And the reason of this is the Wolf-Rayet stars that have such strong stellar winds that they strip out and enrich all their surroundings, which can also explain why these two points are so far apart from each other. We can also compare our values to the solar one, which is denoted by that little small yellow dot. We also plot our CO ratio for the ionic abundances of the carbon against oxygen, and we can see how in this case, our galaxy, which is that one, is also sits very high in relation to other galaxies with similar oxygen abundances, which can also be explained by the presence of these Wolf-Rayet stars. Finally, using our flux ratios, we can also plot a BPT diagram using and denoting the different regions that can be found in the Keeley 2001 and Kaufman 2003 papers. We can see how our galaxy comfortably sits in the star-forming regions in both cases. So these are different conclusions we arrived to, and if you have any question, we are more than happy to answer them.
Questions? Are there any questions? So myself, I'm not familiar with PINEP. So what are the physical ingredients? Is it an optically thin model or like a cloudy-like relative transfer model?
From what I read, I think it actually solves like equilibrium equations to measure like the pop of the state, I think.
Okay. No question.
I think I just missed it. So one of your conclusions is that you got the high CO abundance. And I was just wondering.
It's like CO. I think it's C over O.
Okay. So
no, sorry, no.
Okay.
Yeah.
Thank you. No, just in case I had missed it somehow. Okay. So fair enough. Thank you.
Thank you. Oh, better.
For me, this all looks like a black box on the outside, but do tools like this PINEP software offer any possibility to do an error propagation of some sort?
Oh, yeah. Well, basically, for all the error propagation, we use the uncertainties package in Python and adapted many of the functions, and it basically calculates automatically all the error propagation for all the different functions. You just have to use them in combination with each other, and you can carry out your errors through the entire project. Very easy.
Okay, so thank you.